Morning, everyone. We are going to continue with sampling distributions, and I want to do a little bit more number crunching and formal stuff. So we're going to be looking at two distinct types of questions. One we've pretty much covered, just going to add some more information. And we're going to look at how do you calculate standard error and find confidence intervals when it's a single proportion. And the other thing we're going to look at is we're going to extend that idea to standard error and confidence interval when it's a difference in two proportions. So let's jump right in with the first kind. Well, suppose I have a sample of 1,000 people. It's a nice round number. And I find out the percentage of them who are, what we're going to do, who smoke cigarettes or vape or whatever. And the percentage who smoke was 403. And I would like to take my sample of 1,000, which is a nice simple random sample of adults who are of the age that they can smoke. And I'd like to take this sample of, well, 40.3%. And I would like to create some confidence intervals. Right, so I want to have an interval size for what I think would be the most likely range of values where the true proportion of Americans live. So we're going to find a guy called that guy. It's the standard error. That's essentially the standard deviation of the sampling distribution. And hopefully I won't need to ask, but you'll recognize that formula. And just in case you go looking at other videos online, this guy and this guy are the same guy, because Q is essentially what's left over when you take P away from 1. So in my story here, I guess step 1 would be find the standard error. And it's going to be P hat, which is 403, multiplied by 0.597, hopefully that's right. Yep, all over 1,000. You can, although they're big numbers, you can pretty much do it in one go, which is good. So it's the square root of 0.403 multiplied by 0.597, all divided by 1,000. And the answer I have is 0.016. I'm going to do everything to 3 decimal places right now. Now, step 2 is the creation of the confidence interval. There seems to be an awful lot of them in this textbook. There's one group that is 68, 95, and 99.7%. And then there's the more standard ones, which are 90, 95, and 99% confidence intervals. Now, it depends on which of these you want to find. The formula changes a little bit. The generic formula, right, for all confidence intervals, they all look like this. It's P hat plus a magic z-score times the standard error of P hat. And this Z asterisk, this magic z-score, is a number that gets associated with each of these. So I'm going to give you a little kind of summary list of what these guys look like. If you do a 68%, it's going to be P hat plus or minus, oops, I forgot my minus, 1 standard error. If you do a 95% confidence interval, it's going to be 2 times the standard error. if you do a 99% confidence interval, sorry, 99.7% confidence interval, it's plus or minus 3 standard errors. Those ones get used when you see 1, 2, and 3 standard deviations away from the mean, right? The empirical formula ones. These ones here are much more traditional. And so you have a 90% confidence interval. In this case, got my little number here, it's 1.65 standard errors. If you do a 95%, technically speaking, it's not actually 2. It is 2 if you round it off, but a more accurate version is 1.96. And then you have a 99%, which isn't quite the same as 99.7, but the last one is this one here, and it's 2.58. And these ones are actually the typical ones that you will see used in medical reports, scientific reports, and so on. These are kind of just warm-up values, but these are the real guys, right? The guys that typically get used. So I want a confidence interval for what I believe the real percentage of people, adults who smoke in America is. So I do have a 90, 95, or 99% choice. I would assume that in the question in the homework, they tell you which one, right? They'll say 95. I think they have a 98, but I don't like that one either, right? 95 and 99. So which one do you want? Just pick one and I'll do it.
99.
99 gets the job. So if I'm going to do a 99% confidence interval, do you think that interval is going to be pretty big or relatively small?
Professor?
Yes.
Ashton just emailed me. He said he's in the waiting room.
Thank you.
Mm-hmm.
I'll find him. Yep, there he is. He's in. Thank you. Okay. If you want to visualize what this looks like, you can imagine this interval is the range of numbers where I'm 90% sure the real answer is. If I want to be 95% sure, doesn't it make sense that you'd have to do a bigger interval to be a little bit more likely to collect the right answer? And if I want to be 99%, do you see it's going to be even larger? And if you can think about it, can you see that works here? 2.58 gets you bigger interval, right? 1.96 gets not as big, and 1.65 gets you less. So in this case, we have a p-hat of 0.403, plus or minus, for a 99%, it's 2.58, and the standard error is 0.016. Now, these numbers here do not change. It doesn't matter how big your sample size is. If you want a 90%, it's 1.65, the standard error. If you want a 95, it's plus or minus 1.96 times the standard error. And if you want a 99%, which is one we're doing right now, it's 2.58. So that's the kind of thing you want on a piece of paper somewhere where it's easy to find. Because I can tell you right now that in your test, you're going to get a question like find the 95% in a confidence interval. So you want to be able to, whatever one it is, you're going to have to be there. So I have 0.403, give or take, 2.58 times 0.016, helps when it's on, 2.58 times 0.016, and I get 0.04121. I'm doing it in 3 decimal places still. If you take that away and add it on, we should get the range. So I have 0.403, take away 0.041, and that gets me 0.362 on one side. And if you go 0.403 and you add a 0.041, you get on the other side a rather pretty decimal. That guy. That's pretty much the answer that goes into WebAssign. I prefer percentages. To me, just percentages are easier to understand. So we're predicting, based on this random sample of 1,000 people, that somewhere between 36 and 44% of all Americans smoke, right? If this was a real story, right? Now, it's a 99% confidence interval, which means I'm 99% sure that this interval probably has it, right? Or at least intervals like it would have it. But it's not 100%, agreed? It could be, you know, it could be 50% for all I know. Couldn't it be as low as 10%? And that's, we live with that in statistics. Oh, see this guy here, the plus or minus fella? Can you remember the name that we give to that in statistics? It's got 3 words. It's called a something, something, something.
Margin of error?
You got it. It's a margin of error. Now, I could imagine I was writing an article in a blog or a newspaper, if there are any newspapers left, and this report had came out, maybe it'd be in the Lancet or something, one of the medical journals, just looking at, you know, what percentage of people are still smoking. You could look at this, and I think if you went and said to people in your article that we're 99% sure that the answer is somewhere between 36 and 44%, they probably would be switched off, because there are just too many numbers going on there and you're thinking, what's going on? They are more likely to say something like this. More than 35%, I'm making a nice round number. Isn't this evidence that more than 35% of adults still smoke? So I could have that as my heading, right? Even today, more than 35% of adults are still smokers. Right? That would be a kind of maybe the theme that my story would go. On the other hand, couldn't I say there's evidence to show that less than 45%? Do you agree that every single one of these numbers is less than 45? So you can use an interval by the values that are in it, but can't you also use the interval in terms of what's not in it? It's guaranteed to be less than this, or it's guaranteed to be more than that. And sometimes that can be quite interesting information as well. For instance, if we did an election and we got that answer, that the percentage of people who were going to vote the Green Party was somewhere between 14 and 25%, couldn't we say that the Green Party isn't going to win the election? That would be one. Couldn't I say more than 10% of Americans are going to vote for the Green Party, or less than 25, right? There's 3 ways of phrasing that. If it was a different election, I said this is a Democrat, couldn't you say the Democrat's going to win the election? That's your prediction based on the evidence. And you could even say that more than 52% are going to vote Democrat, or whatever it might be. Another election. Suppose this was the Republican, just to be different. Is the Republican going to win the election?
Maybe.
Maybe. Is his opponent, the Democrat, going to win the election? Maybe. Right, it's a two-party, we'll assume it's a two-party race. In fact, isn't that the one where they say too close to call? Yeah, this state is a close run thing. Could be a Democrat, could be a Republican, we can't really tell. And that's kind of the end of the process for calculating a standard error and a single proportion. So we're now going to move on to a new guy. How to find the standard error and confidence interval for the difference in two proportions. So we need a story for that. In this story, there are actually two different distinct groups. In this group, it's going to be males and females. Right? And we're going to ask them some question like, oh, do you smoke? Right? Let's suppose we ask that question again. And in the males, N1 was 500 people. So the sample was 500. And P1 hat, 150 of them said that they smoked in some way. And that ends up being 0.3. And then we got a totally different one of self-identified females, and we asked them. And it's quite common that both samples are the same size, but they don't need to be. So I'm going to be awkward and pick a different sample size. And I'm going to pick 700. And out of those 700, 200 said that they smoked. And I'll round this off to 3 decimal places. Now, the kind of question that we might be interested in asking here is there a distinct difference between males and females? Right? Do males smoke more or less than females? Well, superficially at least, would you say that there's evidence that the males tend to smoke a little bit higher percentage, right? 30 against 28. But is it not also possible that these numbers could just have happened by the randomness of samples? You know, if I took another sample of 700, couldn't this end up being 0.32? If I took another sample of 700, it could be 0.35. If you took another one, it could be 0.14, right? They vary. Right? Every sample's different. There's a little randomness in it. And the same thing's true about the males. So what we're looking for is, what's the difference between these? And we want to find a confidence interval for it. And then once we've got that confidence interval, we can then answer the question, is there evidence to prove that there is a difference between the two? Right. So we're going to come up with a statistic. And the statistic I'm going to use is P1 take a B to P2. Would you agree that would be a good way of telling if there's a difference? Because if there wasn't a difference, shouldn't that answer be down close to 0? Now, in this case, the P1 is 0.3 and the P2 is that guy. So we are getting 0.014. I don't know why I'm slightly excited. I'll put a bubble around it. There we go. And we are going to find a confidence interval for the difference, right? So we're not going to find a confidence interval for this one and another different confidence interval for that one, and then kind of compare them. We're going to make one single confidence interval for the difference between them, right? Now, suppose that I get that confidence interval and all the numbers are positive, right? So whatever it is, it's 0.01, 0.03, right? If they're all positive, does it not mean P1's bigger than P2? Wouldn't that be the evidence? That's the conclusion that you'd make, right? Does that make sense? That if the difference is positive, P1 must be bigger than P2, right? Because if the difference is positive, P1 has to be the big guy, right? In a different world, suppose that they were all negative numbers. Then wouldn't this be evidence that P2 is bigger than P1? Does that make sense? That if the difference is negative, the second guy's the biggest, right? We're only interested in which one's bigger than the other, right? So the third possibility, of course, is probably the one that happens most often. Couldn't you get an interval that had a negative on one side and a positive on the other? In that case, we haven't got any real evidence. We don't know. They could be equal. One could be bigger than the other. One could be less than the other. We didn't get any significant data out of that. And unfortunately, that happens. You spend a lot of money, and at the end of the day, you don't really have evidence. Right, so back to this guy. The fact that this is positive, would you agree this is leaning towards the P1's bigger than P2? I'd be amazed if this somehow proved the reverse was true, right? I can't see how that could even happen. But it doesn't guarantee that it's bigger, not yet. We have to figure out the interval, right? Which means I need to find a guy called the standard error. And you are not going to like this formula one bit. It starts off the way you think it's going to start off. Can you remember P hat, Q hat over N? Remember that guy? It looks like that. It's P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2. Does it kind of sort of make sense why that formula would be a bit from each added together? But saying that, isn't it one ugly looking formula? So here goes. The standard error of P1 hat, take away P2 hat, is the square root of P1 hat, 0.3, the other guy is 0.7, divided by 500, plus P2, it's 0.286, 0.714 out of 700. I'm going to go for glory here. Square root. 0.3 times 0.7 divided by 500. Add 0.286 times 0.714 divided by 700. And the answer that we got is 0.027, because I'm working in 3 decimal places. So we now have the standard error. And I want the confidence interval. And I'm picking it this time. I'm going to pick a 90% confidence interval. Now, the formula for getting it is going to be P1 hat, take away P2 hat, plus or minus the magic z-score for 90%. It's still 1.65. Right? The magic z-scores don't change just because the story's changed. Times the standard error of P1 hat, take away P2 hat. Now, if I wanted a 99% confidence interval, do you know the only thing I would change is that this number would be changed into 2.58. And if I wanted a 95, wouldn't I just change this number into a 1.96? So at least there's some consistency between 1 and 2 and the difference in 2 proportions. Now, the difference between these two guys is 0.014. And the standard error we got a little minute ago is 0.027. So I have 0.014 plus or minus 1.65 times 0.027. And the answer I get is 0.045. And that's going to come out as 0.014, take away 0.045. And so on this side, it's negative 0.031, and then 0.059 on the other side. And that's what WebAssign would like. Negative 3.1% up to 5.9%. So what we can say here is that there isn't any significant difference between males and females smoking habits. Would you agree there's negative answers and positive answers? We can't really distinguish between the two. Are we comfortable with the process? Because all that's going to change from this point onwards is the story, right? The next story, it won't be people smoking. Next story, it might be Republicans and Democrats and something to do with each, right? Whether they smoke or something, right? Or the next story might be, they've got a couple of questions to do with obesity in urban children and obesity in rural children and things like that. Okay, so if you hold on for a few moments, I have 5, 10, 5, 10. I have 25 people to take part in a version of that. I'm going to cheat a little bit or I'll never get any evidence. Oh, before I forget, because it just came to me, that there are certain things I haven't mentioned yet. So let me just return back to the data. There are tests on whether or not you're even allowed to do this. Can you remember the NP, NQ have to be bigger than or equal to 10? Remember that? It's true for these. All you do is the N1, P1, N1, Q1, N2, P1, P2, N2, Q2. God, that's a lot to say. Basically, doesn't everything have to be bigger than or equal to 10? That's essentially it, right? So we can't really do that test unless it's true. But I'm going to cheat. You don't know it right now, but every single one of you is actually 100 people. So that when I collect my sample, I'm going to pretend that when you say yes to whatever the question is, right, that you're actually 100 people. Otherwise, I won't be able to do the test because NP will never be 10 for a class this small, right? So pretend that that little lie was like actually okay. So we need a question. Oh, let's do the classic. Pepsi or Coke, right? So you can only pick one. If you like both, you pick the one you like tiny little bit more. And we're going to ask the question in terms of Pepsi. So do you like Pepsi? Okay, is going to be the question. And Celia, what are you drinking right now? I don't think we need to get her vote. I think I know what it is, right? But the rest of us are going to do it. So we're going to have self-identified males and self-identified females. And we're going to do the Pepsi Coke thing, right? So I should put my vote in as well.
What if I've never had either?
Don't vote. Just be a non-responder, right? That'll just make my life easy. Just don't vote. Right, so self-identified males, can you do the thumbs up thingy and we'll count you as how many like Pepsi? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. I'm 7. That's 7. 1, 2, 3. 7 out of 10. Okay. Same question. Thumbs up or the icon thing? Pepsi people in the female world. 1, 2. Wow. 1, 2, 3, 4, 5, 6, 7. Oh, there was 3. Somebody came in late. 7, 8, 9, 10, 11. Okay. I guess we have some non-responders. That's fine. Okay, so switch back to our story. Now, I went and said that everybody was 100, right? So that's 700 out of 1,000. And that's 3 out of that. Right, so we got a 0.7 and a point, oh, it's not 0.3, is it? 300 divided by 1,100. 0.273. This is better than I thought. Just looking at the raw data, would you agree there seems to be a male-female split on Pepsi? That males seem to like Pepsi more than females, right? Does that seem reasonable based on the data? So what we're going to do now is we're going to go through the process of finding a confidence interval for it. So P1 hat is 0.7, and that sample size was 1,000. And the second sample was 1,100, and it came out about 27%. So the statistic we're going to use is this guy, which is 0.7, take away 0.273, which ends up being 0.427. Okay. Now the standard error is going to be the square root of 0.7, 0.3 over 1,000. That's P1 hat, Q1 hat over N1. Added to 0.273, 0.727 over 1,100. So square root 0.7 times 0.3 divided by 1,000. Oops. I have to do that again. I forgot the second half. 0.7 times 0.3 divided by 1,000 plus 0.273 times 0.727 divided by 1,100. And the answer I get is 0.019, which becomes 20 if you round it off. Okay, let's go for, oh, you tell me, what percentage confidence interval do you want? A 90, 95, 99? What do you want?
99.
Another 99 it is then. So based on this one, if I get evidence, isn't that really strong evidence? Like I'm 99% sure of what I've just said is true, right? If I suspect that's going to be the case. So it's going to be this guy plus or minus the magic number for 99 is 2.58 times the standard error. Are we comfortable with that guy? Okay, so take away, blah, blah, blah. I've lost my guy. Where is it? Here it is. 0.427 plus or minus 2.58 times essentially that number. 0.427 plus or minus 2.58 times 0.02, which is plus or minus 0. Check that again. 2.58 times 0.02, 0.052. And let's see what we get. Take that away from that. 0.427, take away 0.052, and I get nothing 0.375. And then if I add it, I get a 9, 7, and a 4. So the interval is somewhere in the region 37.5 up to 47.9%. So the difference between males and females in Pepsi is that it's a clear positive. Agreed? Definitely all positive. So my conclusion here is that males like Pepsi more than females. And couldn't I quantify it a little bit and say, not only do males like Pepsi more than females, but they like it by at least 37% more. Yeah, just taking a nice round number, right? So you could have, well, I guess if this was really true, wouldn't Pepsi be out tomorrow doing a big advert? 37% more males like Pepsi than females. I'm not sure that's a good advert now I'm thinking about it, because won't Coca-Cola do the other one? Because from the other perspective, doesn't that mean females like Coke better than Pepsi? Right? It works both ways. Interesting result. I don't think there's anything magic about it. It could just be the randomness of this class. Right? But we do have evidence. So, one last shot at this guy. And then when I see you tomorrow, we'll just look at some homework questions. So I'm making one up for you. Let's have Scotland against America. And we went and asked in Scotland, (1,000 males, and in America, we asked 1,000 males as well. So we kept the sample same size. And we asked how many of them were drunk in the last week. And in Scotland, it was 650. And in America, totally made up numbers, it was 600. And we are going to, or you are going to create a 95% confidence interval for it. And you have got 3 minutes to do it. And I'll write down your formula for you. For a 90%, it's going to be 1.65. Oh, P1 hat, take away P2 hat. There we go. Plus or minus, start again. P1 hat, take away P2 hat, plus or minus 1.65 times the standard error. And the standard error is that guy. Okay, so you've got 3 minutes from there. No pressure, go for it. Last few seconds. Okay, let's go through this, see where we go. I think finding the percentage of Scots who'd been drunk and the percentage of American adults was pretty straightforward. The difference between them, I seem to be picking questions where the first one's always biggest. You know, it doesn't need to be. Couldn't you have a 0.3 take away a 0.5? You know, it happens both ways. The standard error one is probably going to be the ugliest one to calculate. Anyway, it's a 0.65, 0.35 over 1,000 plus a 0.6, 0.4 also over 1,000. It would save me a lot of grief if someone's actually comfortable enough to share what did that come to. And if we get two people with the same answer, I'll use it.
0.022.
Did I get a nod off anybody for that? 0.022. A thumbs up would do. You can't give a nod. I may be getting thumbs up. I'm going to have to go and have a look and see if anybody else is here. Oh, Zoom's been a pain in the butt. Come on, Zoom. Right, did anybody get 0.022? Did you get something else then? Because maybe you get another number and we have to use that.
I don't know if everybody else got this as wrong, but I got 0.00022.
Oh, interesting. Right, let's find out. The fact that two twos are the same sounds to me like it might simply just be a calculator issue. Right, so here goes. Square root of 0.65 times 0.35 divided by 1,000 plus 0.6 times 0.4. And it does, oops. There we go. Divided by 1,000. Now it doesn't matter which one of you two ends up being right. It's just, okay, we got a 0.022.
I forgot the square root. That's my bad.
That would be it. That's all it takes. So the difference between these two, which I actually haven't calculated yet, is 0.005. So it's 0.05 with a 1.65 times 0.022 ends up being 0.05, give or take. A 1.65 multiplied by 0.022 comes out to be 0.036 to my usual 3 decimal place rule. So that's 0.014 or 0.086, which is 1.4% all the way up to maybe 8.6%. So we have evidence that Scottish people get drunk more often than Americans. And the evidence is that the entire confidence interval for the difference is got nothing but positive numbers. And the fact that there's nothing but positive numbers means that this difference is positive. And if this difference is positive, P1 has to be bigger than P2. That's kind of the logic behind it. Now, as far as percentages go, it's, yes, it is significant statistically, but if we round that off, it's somewhere between 1 and 9%, right? So it could be negligible. Would you agree a 1% difference between two groups is hardly worth worrying about? On the other extreme, it could be as high as 9. And that would be quite interesting. One of the things they do when they say statistically significant is that they don't very often tell you anything extra. They just said, oh, they've conducted a trial and it's statistically significant that white Scottish guys get into fights more often than white Spanish guys. Now, statistically significant just meant that the interval was all positive, right? But suppose the interval was 0.003% to 0.004%. In reality, isn't that difference statistically significant, but in reality, totally unimportant, right? So there is a difference between statistically significant and important. An important difference is one where the difference is a big number, right? Or at least reasonably large. Can you imagine that you might not always get that result? Can you imagine you could get a ridiculously small interval, but still significant statistically because they're all positive? Right. So if you went and said to me that I have a statistically significant higher chance of catching COVID if I don't wear a mask than when I do, that can be correct. If the difference in my catching it is this, does wearing a mask really matter? No. Now, I'm not saying this is real data. I don't know what the real data is. But here's a question for you. Does anybody know the real data? Have you ever seen an article that said, this is the percentage chance you will catch COVID with a mask, this is the percentage chance you'll catch it without a mask, or this is the percentage chance you will give someone COVID with a mask, and this is the percentage chance you'll give someone without it? Because I'm hearing a lot of people telling me that they're going to the science, and I love science, but what I don't hear anywhere is a number. But maybe I've missed it. Has anybody seen a number? We're just being told that it's a good idea.
Don't open this can of worms.
Well, I've owned it. I'm just putting this out here as a devil's advocate. Do you see why you have to be aware of statistics? Because statistics makes you think in a different way than a typical human being would think. Oh, I've been told that there's evidence and it's statistically significant, so I better do it. Well, let's look into that a little bit more. I don't know what the data is. Do you know, it could be ridiculous. I mean, it could be 57 to 99%, in which case everybody better wear masks.